All right, but just a reminder that you don't actually have to go it alone because you do have access to the online lectures and my YouTube channel. You can check Canvas for that link. But also, I do post these for every semester, and I do teach this class regularly. So if, for example, you're working ahead and you want to do ZScores because this upcoming week, you just have a paper due or something, you want to get it out of the way for whatever reason, but you're finding it quite challenging, you can go to my previous lectures, and I do tweak them every single semester, but ZScores are ZScores, so you can go to those previous semesters, watch those videos, and get yourself the help that you need. So a lot of resources, a lot of options, especially on some things that just cannot be explained via email. Right? It's kind of hard, as you're going to see today, to do the multi-step Z-score via email, but there are, again, videos that you can watch in my channel from previous semesters to help get you ready. All right, so today's class, week 4, class number 1, we've been working through chapter 2, and we started off with the mean and measures of central tendency, and then we used the concept of the mean to define and be able to calculate standard deviation and variance. And now we're going to complete chapter 2 by using the mean and the standard deviation in order to calculate the very useful Z-score. So as you can see, the common theme in this class, your skills keep building on the last thing that we've learned. So this is a good time to kind of take inventory of your skills. And if you're at all struggling with the mean, or you're at all struggling with standard deviation, then Z-scores are going to be very, very difficult. But if you've got the mean down, if you've got standard deviation down, then Z-scores is literally just one more step that'll be pretty straightforward. So take an inventory, see where you're at. If you need to do extra work, go back and review things. Make sure you're taking care of those skills as we continue to build. So we are going into Z-scores. Here we go, that is today's class. But before we get to that, just a real quick announcement. Oh, yeah. Before we get to that, just a real quick announcement. No wonder it's not working. There we go. Just a real quick announcement. We got exam number 1 coming up next week. So that is going to be Tuesday, a week from today. And that'll be during class time. And it's going to be covering chapters 1 and 2. So it will be covering frequency distributions, frequency graphs, frequency tables, order of operations. It'll be covering how to calculate the mean, the median, and the mode. It'll be covering how to calculate some squared deviations, standard deviation, and variance. Sample only. We're not going to be doing population on the exam, just samples. And then also it'll be covering how to calculate Z-scores and standardized scores, what we're going to be doing today. So there's not going to be any surprises. It's basically everything that we've covered so far is going to be on exam number 1. All right, so that you know what the exam will be like so you can best prepare for it, it is a completely computational exam. What that means is that there will be no conceptual questions. There will be nothing like, what is the mean? Which of these is the best description of standard deviation? There won't be any questions like that. It will literally be, here's your situation, calculate these things. Here's this set of data, calculate these things. So it's a completely computational exam. It's going to be available in Canvas as an Excel sheet. So in the morning, I'll publish it right at the beginning of the class. You'll come in, you'll download the Excel sheet, you'll enable editing, and then you will save it once you're complete and upload it to Canvas assignments to the Exam 1 assignment tab, your completed Excel sheet. So make sure that you are familiar with how to save it, either to a USB drive or to one of your IU drives. Know where to find that, how to link it, and upload it through Canvas, because that's what we'll be doing for the exam. There's going to be 7 questions, and remember that it will be open book, which I want to be very clear means open everything except other people. So that is the only restriction. You have to do your own work. You can't be on your computer Skyping with the chair of the statistics department at MIT. It has to be your own work. But whatever else you need to do this, feel free to bring in those resources and access them during the exam. So if you want to consult your e-text, feel free. If you want to log into Canvas and take a look at the student PowerPoint files, absolutely. If you want to open up one of your old Excel sheets to see where the, what the formulas are, absolutely do that. If you want to prepare step-by-step instructions on how to do each of those calculations that we've been working on these past weeks, do that as well. So this is really going to mimic kind of the real-world environment that we're preparing you for, which is not do you have it memorized, but rather can you do it. So I don't care if you have it memorized or if you have it written down right next to you. All I care is that at the end of the exam, have you done it? Have you gotten the correct answers? So it's going to be open book. And just to be clear on this, it has to be completed in class. So during class, I'll have assigned an in sheet that I'm going to pass around to make sure that you're doing it in class. And that's just to make sure that you're doing it under exam conditions, that you are working alone, that it is your own work. So don't at all think, and this has happened very rarely, but I don't want anybody to make this error. Don't think that because it's online, you can just stay at home, access it online, and then complete it. It will not count unless you're in this room completing it, or if you need other accommodations, wherever it is, but it has to be completed under these exam conditions. All right, any questions on the exam? All right, so it will look, if you need a sort of example of what you can expect, it will look almost exactly like the worksheets, Excel sheets that we do in class. So you're going to see the, the sets of data, you're going to have room to do your formulas, you're going to see the yellow answer cells where you have to put your final result. The only difference is it's not going to have those green answer cells. I'm going to add those later when I grade your exam. All right, and to help us prepare for exam number one, every class before an exam is going to be a review session. So next class, this Thursday, we're going to have a review session. And the way that this review session works, it's an open review session. And what that means is that it's student driven. So I will have nothing specific prepared. I don't know what your needs are to get ready for the exam. That's why it's open. So come in, bring your questions. Can I see Z-scores one more time? What was the formula in Excel for standard deviation? I'm having a real trouble reading this frequency distribution graph. Can you show me, how to do this? So we'll go over anything that you might need during that open review session, but it is completely student driven. So sometimes I get a whole bunch of questions and we have a very active review session. Sometimes I'm just sitting here at the front of the class waiting for a question. Either way, whatever you need, we're going to be doing that next class. Now because of that, it's also completely optional. So if you feel your time will be better used, maybe preparing on your own, maybe catching up on some of your work during that hour and 15 minutes, feel free. It's completely optional. But I will be here to answer any questions or do any demonstrations and get people ready if you want to take advantage of that review session. So that's next class, the class right before the exam. All right, any final questions about exam number one? All right. Okay, so we are getting very, very close to being able to do some inferential statistics. We are getting very close to being able to do the cool stuff that you probably thought a statistics course was going to be all about, but we need just a few more pieces. And one of those pieces, one of the crucial pieces, is going to be what we covered today, which is Z-scores. So Z-scores are often, I'll just give you fair warning on this, they are often one of the first roadblocks that a student sort of encounters. So usually, as we progress, frequency distribution, everybody's on board. The mean, everybody's on board. Standard deviation, everybody's on board. The Z-score is the first hurdle where a lot of students get over on their first try, some students don't. So just be aware of that. It might be more challenging than what we've encountered so far, but it is absolutely an essential skill. We're going to use Z-scores and Z-score-like concepts when we go into doing the real cool stuff, where we can take a look at data and decide, are these real differences or are they fluke? does my treatment actually work, or does my treatment do nothing? So we still got just a little bit more work on your journey towards that. So let's set up what we're going to be looking at today with an example. Let's say that you're a clinical psychologist and you specialize in child psychology. And let's say that a parent brings their son to you and says, you know what, I think he might have behavioral problems. I need you to take a look at him. Right? I don't know if this is normal levels of these behaviors. So you ask the parent, you know, what seems to be the issues? And she says, you know, Jimmy, he's very active. Very, very active. Like just super active all the time, bouncing off the couch. Can't get him to sit down, can't get him to sit still. In addition to that, there's another symptom. He has trouble paying attention. So not only is he very active, but he also has trouble paying attention, easily distracted. And as a clinical psychologist, one of the first things that you would need to do is to test Jimmy. You can't just take the word of the parent and say, all right, well, Jimmy must have these symptoms. You have to assess Jimmy somehow, and we have assessment tools that we can use to measure the amount of Jimmy's behaviors. And then the next thing that's crucial is oftentimes in a treatment program, the easiest way to fail a treatment program is to try everything at once. We're going to fix everything that the client needs or the patient needs all at once. This is like making 10 New Year's Eve resolutions, right? You're not going to do any of them. You're going to fail at all 10. But if you tackle one New Year's Eve resolution, your probability of being successful goes up. So as a clinical psychologist, we would want to take a look at this behavior and we would want to identify which one is the most extreme, which one is the biggest problem, the most outside of normal behavior, and tackle that one first. So we would need a way of identifying what is it that Jimmy is most extreme on. Is it his activity levels that are the most extreme and we'll tackle that first, or is it his attention deficit? Is that most extreme and we'll tackle that first? So we're going to see that in order to do this, we need to make use of Z-scores. So we're going to introduce the idea of Z-scores first and why they're necessary. Then we're going to take a look at how to calculate Z-scores. What are the parts of a Z-score? We're going to take a look at the properties of Z-scores, what makes them so extremely useful. And then we're going to take a look at how to calculate Z-scores from raw scores. We're going to learn how to go back to raw scores from Z-scores so we can exchange it both ways. And then we'll learn a very useful tool, how to create standardized distributions so that people, oftentimes without a statistical background, can understand your Z-scores. And then we'll mention the homework assignment, and we'll have time for practice. All right, so introduction to Z-scores. So back to Jimmy. Let's imagine that I'm that clinical psychologist, and I have an assessment tool that's a lot like the IQ test, but this one is for activity. So this measures your activity Q, right? And let's say that Jimmy scored 80 on the activity Q. That number by itself is meaningless. He scored 80. What does that mean? Is that a high active Q score? Is this is Jimmy very, very active? Is it a low active Q score? What does 80 mean? Well, 80 on its own is meaningless. It means nothing. What we need to do is we need to put it into context. We need to be able to say, well, in the population, this is the range of scores that people get on the active Q. They score from 10 all the way up to 100. There's the distribution of active Q scores in this population. And once you have that context, then you can say, well, that's where Jimmy is. And as we can see, Jimmy is above average, right? And he's all the way up here at 80. He's pretty high. There's only this many people in the population that score higher than Jimmy. Everybody else scores lower. Jimmy has a high active Q. So putting it in context allows us to determine that 80 in this case is actually a high score. However, if this was the distribution here, if 60 was the lowest that people score and 240 is the highest that people typically score, well, now all of a sudden Jimmy is right there. And Jimmy actually has an incredibly low activity level. So number one, we wouldn't want to treat Jimmy for his activity level. If anything, we'd want to increase it. Number two, we probably want to talk to the parents and wonder why they're misperceiving their son's behavior so dramatically. And maybe they're the ones that need, to talk to a professional. But regardless, this same score of 80 means a very low level of activity if this is the frequency distribution of the population for active Q scores. So that's his active Q. So let's say that Jimmy is actually very high on his active Q. And his score of 80 is 25 points above the mean for his active Q. Now, we know that, so we know he's got a high active Q. Now, let's suppose that I give him a second test. And this is another test that I came up with, the ADHD Q. And it works the same way. It's going to see if Jimmy is very high on attention deficit or is he very low on attention deficit. And let's say that I give him this test, and there's his active Q score, and I give him this test, and there's his ADHD Q score. So he scored 70 on the ADHD Q. What does that actually mean? What does 70 mean? Is Jimmy's score on the ADHD Q more extreme than his active Q score? Or is his active Q score more extreme than his ADHD Q score? Now that might seem like a weird question to ask because once again, going all the way back to elementary school math class, we know that 80 is bigger than 70. The number 80 is bigger than the number 70. But just like 80 was meaningless unless you put it into context, so is 70. 70 is meaningless unless you put it into context, and you have to put it into its own context. So let's say that this is the distribution of ADHD Q scores in our population. And we'll split up the two distributions. So this is the distribution of ADHD Q scores in our population. Jimmy scored a 70. This is the distribution of active Q scores in our population. Jimmy scored an 80. So even though 80 is bigger than 70, we can see here that whereas his score of 80 is pretty high, but there's still individuals that score higher than that in our population, his score of 70 on the ADHD Q is basically the most extreme in the population. He is very high, very extreme in this score. 70 on the ADHD Q is incredibly high. And that should be the behavioral issue that we tackle first. That should be the one that we tackle first. And again, we can only understand this by placing it into its context. So that's why we need Z-scores. So if we want to be able to compare scores, if we want to be able to understand scores, is this a high score or is this a low score? And if we want to be able to compare scores, compare ADHD Q scores to active Q scores, basically compare apples to oranges, we need to be able to describe them with respect to a known distribution. We need to be able to describe them with respect to a shared distribution, and that's what Z-scores allows us to do. Z-scores allows us, among other things, to make exactly these types of comparisons. All right, so any questions on the need for Z-scores so far? All right, so let's take a look a little bit more at what Z-scores are. So a Z-score is simply a transformed raw score. It's simply a transformation that changes your raw score into what we call Z-scores. So it's nothing more than taking a set of Z-scores and saying, I'm going to apply this formula to you, and I'm going to change you into these Z-scores. So apt analogy for this, if you've ever traveled to a foreign country, this is exactly like exchanging your money. So if you're going to Mexico, you take your US dollars, you transform them into pesos. If you're going to Europe, you take your American dollars, you transform them into euros. And there's some formula that they use to go from US dollars to euros, and there's another formula they use to go back from euros to US dollars. Same thing here with Z-scores. We take our raw scores, and we use that formula, and we just transform them into Z-scores. And as you'll see here, this raw score of 8 transformed into a Z-score of 0.19. This raw score of 8 also transformed into a Z-score of 0.19. This raw score of 9 transformed into a z-score of 0.57, 4 transformed into minus 1.33. So every single score transforms into a very specific z-score. And the power of the z-scores comes from what this transformation actually does. So it's a very specific transformation that is extremely useful because of the two things that it does. So the first thing, the two things that it does is it moves your distribution of scores. It takes your distribution and moves it to a very specific spot, and then it either stretches out or squeezes in your distribution so that it has a specific amount of variability. So let's take a look at that. So this is a frequency distribution of those scores that we just saw. So this frequency distribution of raw scores here, it has a mean. It's got a mean of about 7.5. What a z-score does is it transforms these raw scores. It changes those US dollars into euros. It transforms these raw scores so that the new mean of your distribution is 0. So that's the first thing. It moves the center of your distribution to a mean of 0. The second thing that it does is it takes your distribution, and if it's too wide, it squeezes it down to a standard deviation of 1. Or if it's too narrow, it'll stretch it out to a standard deviation of 1. So in this case, our distribution was too wide, so when it got transformed into a z-score, it squeezed it down so that this now has a standard deviation of 1, and it's got a mean of 0. And that's what a z-score does for any distribution. So we have this distribution here. It has a mean, this is a raw distribution. It has a mean of just over 6, looks like about 6.5. If we transform this into a z-score, it moves the distribution so the mean is 0. And in this case, it stretches the distribution out so that the standard deviation is equal to 1. And it will do this for any distribution. Every frequency distribution of raw scores has a certain mean. Every frequency distribution of raw scores has a certain standard deviation. Every frequency distribution of raw scores can be transformed into a distribution of z-scores that has a mean of 0 and a standard deviation of 1. And it doesn't matter what your distribution looks like. It doesn't matter how wide or narrow it is. Every distribution can be changed into a z-score with a mean of 0 and a standard deviation equal to 1. So it moves the distribution so that its center is at 0, its center of mass, its mean is at 0, and then it either stretches or squeezes the distribution so that the standard deviation equals 1. And that is that idea of a shared distribution. All z-score distributions share a common mean, 0. All z-score distributions share a common variability, standard deviation of 1. All right, so that's what z-scores are, but they're extremely useful because of that shared distribution. So when you have a z-score, that z-score actually tells you the location of your score within that distribution. It actually tells you where your score is in that distribution just by the number. So whereas, whereas a raw score of 80 is meaningless, a z-score of minus 1.71 is meaningful. It tells you everything you need to know. So what does it say? Well, there's two pieces of information it tells you. First off, it gives you the sign. The sign tells you if your score is above the mean or if your score is below the mean. If it's positive, it's above the mean. If it's negative, your score is below the mean. So if I tell you that Jimmy has an active Q of 80, you don't know if he's above average on activity. You don't know if he's below average on activity. It's meaningless. If I tell you that the z-score for his activity is 1.33, you immediately know he's above the mean. He's above average. If I tell you that the z-score for his activity is minus 1.71, you immediately know he's below average. So if you get a z-score that's positive, that score is above the average. If you get a z-score that's negative, that score is below the average, because the mean of every z-score distribution is 0. So that's the first thing That a z-score will tell you. The second thing is the actual number. The number gives you information, and that is the distance from the mean to your z-score in steps of standard deviation. So if you have a z-score of minus 1.7, that is below the mean, and it's minus 1.7 standard deviations below the mean. If you got a z-score that's positive 1.33, that is above the mean, and it's 1 1/3 standard deviations above the mean. So the larger the number, the higher you are, or the further away you are from the mean. If it's a larger positive number, you're higher than the average. If it's a larger negative number, you're lower than the average. And the distance is scaled in terms of that standard deviation. Every step, every whole number is one more standard deviation away from the mean. So when you get a score of minus 1.71, it tells you everything you need to know. It lets you know that it's below the mean, and it's almost 2 standard deviations below the mean. It's pretty far away. If you get a standard deviation, a z-score of 0.19, you know that it's above the mean, but it's almost right at the mean. It's like 1/5 of a standard deviation above the mean. So there's a lot of information in that one number. All right, so we got a lot of information. We got this incredibly useful z-score. What do we do? How do we get it? How do we actually make it to get these z-scores? So we're going to take a look at the calculation of z-scores, and the formula for transforming your raw scores into z-scores is the same. It's similar, for a population and a sample. Here it is for a population. The first thing we have, we got a numerator and a denominator, so there's the full formula there. The top of it is your raw score minus the mean. So the top of the z-score formula is your raw score minus the mean. If you recognize this as a deviation, that's awesome. That's beyond where we need to be right now. But some of you might say, hey, that's the definition of a deviation we saw last time. That's awesome. That's a deviation. And then to make it a z-score, we divide it by the standard deviation. And that dividing by the standard deviation is what scales or squeezes and stretches your z-score. So the top part gets the mean to 0. The bottom part is the stretching and the squeezing part. So that's for a population, the z-score for a population. We have your raw score minus your population mean, and all of that divided by your standard deviation. For a sample, it's the exact same idea, just the terms are a little bit different. So for a sample, we have your raw score minus your sample mean, all of that divided by your sample standard deviation. So it's the exact same idea. Deviation on top, that sets your mean to equal 0. Standard deviation on the denominator, the bottom, that's what stretches or squeezes your distribution. And that's the formula. So if you want to calculate a z-score for any particular raw score, you find the mean of all the raw scores, you find the standard deviation of all the raw scores, and you take each raw score minus the mean divided by the standard deviation. That'll transform your raw score into your z-score. All right, so that's the calculation, and we're going to see how to do this in Excel, so we can do this rather quickly. But before we get to that, let's take a look now at some more details about the properties of these z-scores. What happens to your raw scores after this transformation? So again, these z-scores, they're just transformed raw scores. They're just these raw scores exchanged into another format. So why are they so useful? We've already alluded to these, but let's make it explicit one more time. Your z-scores tell you exactly where your score is within the distribution. So the z-score tells you exactly where your original score is within its distribution. And your z-score allows you to compare that score to any other score, because any other score can be transformed into a z-score. And that's one of the big functions of z-scores, especially in clinical psychology, is the ability to compare how extreme different behaviors are. So I'll give you another example. Let's say that you go into educational psychology and you are helping students in a high school kind of plot their career path, kind of think about what is it that I should be pursuing, where do my skills lie, where are my aptitudes, what should I focus my skills on. So let's say that a student comes to you and they are either thinking about pursuing math or they're thinking about pursuing English. Right? So either they're going to pursue a career that's heavy in math or they're going to pursue a career that's heavy in English, heavy in writing. So they come to you and you say, well, let's take a look at your recent quiz scores. Right? I heard you just recently had a quiz in math. I heard you just recently had a quiz in English. Let's take a look at those scores. And you find out that for math, they had a score of 7 on their quiz. So that's them right there. And on English, they had a score of 7 on their quiz. So now you got to compare these two scores so you can advise the student which one are they better at. Are they better at math or are they better at English? In this manner, we can't compare. Number one, they're both 7. Number two, they're on different scales. This is literally comparing apples and oranges, right? There are 2 scales, 2 different tests, 2 different distributions. So we can't compare them directly, but what we can do is we can put them into a common distribution. We can put them into a z-score. So we transform the math scores into a z-score. And that's what the student's math z-score is. We transform, and it's just below 0. So this student is below average on their math skills. We transform their English scores into z-scores. And their z-score on English is actually about 1.5. So they're 1.5 standard deviations better than average on English. And now we can compare. Now we can tell this student, look, you're below average on math. So it's going to be very challenging for you to pursue a career in mathematics. But you are highly above average in English. And that 7 in math means below average. That 7 in English means highly above average. So again, you can't compare the 7 to 7, but you can compare the z-scores because they share a distribution. They share a mean of 0, standard deviation of 1. So we're able to compare those, and you're able to guide the student and make them aware of where they excel compared to the population versus where they struggle. All right, so that's one of the reasons that they're useful. What properties do they have? We've alluded to these so far, but they change the distribution to a new mean and a new standard deviation. But what they don't do is they don't change the shape of your distribution other than stretching it or squeezing it. So you see here, if we have a distribution that has 2 peaks in the original distribution, our z-score distribution also has 2 peaks. This is the same shape as this, just squeezed. If our z-score distribution, our original distribution has 1 peak, our z-score distribution also has 1 peak, so the shape is maintained. Other properties that they have, the mean of your z-score distribution is always equal to 0. So if you are ever talking to somebody and they ask you, you just took a test. What was your score? And you say, I got a z-score of 1.5. If they ask you, what was the mean of the z-scores? They don't know z-scores because the mean of the z-scores is always equal to 0. So the mean of your z-scores always equal to 0, and that is because it uses these deviations to calculate your z-scores. So if you remember, if you add up all your deviations, you get 0. That's why we had to square them last time when we were doing variance. So when you add up all your z-scores, you're going to get 0. So the mean of your z-scores is always equal to 0. And then the other properties that they have is your standard deviation for your z-scores always equal to 1. And that is because of that denominator. That is because you scale your z-scores. You either stretch them or you squeeze them in order to get their standard deviation equal to 1. So we're going to see how you can take advantage of this, especially when you're doing for example, your homework, your exam, and just in real life. This is going to give us the opportunity to not only understand z-scores, but also to double check our calculations make sure everything is going well. All right. So we saw the calculation where we go from your raw scores to z-scores. Sometimes you also want to go from your z-scores back to your raw scores. So sometimes you're starting with a z-score and you want to know how to get back to that raw score. And for that, we just have to rearrange this equation. So that's your equation for z-scores. So if we solve for the raw score, if we solve for x there, a little cross multiplication, bring that mean on the other side, and that's how you recover a raw score. So if you're starting with a z-score, if somebody says, oh, my z-score is 1.5, and they say, well, what was your actual raw score? You can say, oh, well, we just take the mean plus that 1.5 multiplied by the standard deviation of the sample, and that will recover your z-score. Sorry, your raw score. And this recovery of the raw score allows us to do one more really useful thing with z-scores, and that is it allows us to create our own distributions. It allows us to create our own, just say it one more time, our own distributions to be whatever it is that we want them to be. And these distributions are sometimes called standardized distributions. So in our culture, probably the most popular or famous standardized distribution is the distribution of IQ scores. IQ scores are standardized so that the mean of an IQ score is 100 and the standard deviation is 15. So that is just something that people who are familiar with IQ scores, even a little bit, will know. And it's easier for them to understand IQ scores as IQ scores than as z-scores. So if you tell somebody, oh, I tested your child, and they got their IQ score, the z-score for it was 2. They got a z-score of 2 on their IQ test. The parent might not understand what that means. They might not know what a z-score is. But if you transform it into the standardized score and you say, oh, I tested them on the IQ test and they got 130. A lot of people will know, oh, okay, that's pretty high. 100 is average, 140 is genius level. Wow, 130, awesome. So sometimes in order to communicate effectively, we want to change our z-scores into these standardized scores. So that's the last thing we're going to take a look at here before we go to the calculations. How do you get to that standardized score? How do you get to those distributions that are simpler to deal with, especially if you don't have a statistics background? Well, there's 2 steps for taking any raw score and transforming it into a standardized score. The first step is you take your original raw scores and you transform them into z-scores. So that's the first thing. Z-scores is kind of like that universal exchange, right? It's sort of like that universal distribution that everybody can get to. So you take your raw scores, you transform them into z-scores. So if that's our distribution of raw scores, move number 1 is we take them and we transform them into z-scores. So now we have our z-scores, then we're ready for move number 2. And move number 2 is you take your z-scores and you change those into new standardized raw scores. And here's the big thing to remember. With a specific mean and a specific standard deviation. So when you're creating standardized scores, you need to know what mean you want. And you need to know what standard deviation you want. So if I'm creating standardized scores to look like IQ scores, I'm going to want a mean of 100 and I'm going to want a standard deviation of 15. And you absolutely need to have that information. Sometimes students forget about this and then you have missing information and it's impossible to calculate. If you're doing a standardized score, find that information. It'll be in the question somewhere. You absolutely need to have it. You need to have that new mean that you want and that new standard deviation. All right, so for example, let's say that we have this distribution here. It had a mean of about 7.5. And we want a new mean. We want a mean of 30. And we want a new standard deviation. We want a standard deviation of 10. We need to have that information. Then we can put it into our formula for getting raw scores from Z-scores, and we can transform these Z-scores into this new distribution that has a mean of 30 and a standard deviation of 10. So make sure, that's the biggest hiccup I find that students encounter when they're trying to do standardized scores. They forget about the new mean and the new standard deviation, and you absolutely need that information. All right, so let's put this into practice, and we will calculate out some Z-scores, and I will show you a technique, a very simple technique for calculating out Z-scores so you can take advantage of your copy and paste techniques that you've been developing. So let us go to that Excel sheet. So the Excel sheet that you're looking for, let me just exit out of this. All right, so you are looking for this Excel sheet. So it's week 4, class 1, practice, chapter 2, Z-scores. And we're going to concentrate on this question right here. And while we're on the subject, this homework assignment for Z-scores, that is available not through the MyLab. It's one of the rare ones that's available through Canvas. It's in the files section. You can find Excel homework. You will download the homework and then upload it to Canvas. But let's get to Z-scores right now. So given the following sample of 10 scores, so that N means how many scores do you have? For each individual score, calculate the following. We're going to want to calculate Z-scores, and we're going to want to calculate a new standardized set of scores with a mean of 40 and a standard deviation of 10. All right, so the first thing I'm going to do is I'm going to show you what not to do, so you don't make this mistake. So don't do this on your own. But if you remember the formula, there we go. The formula for a Z-score, and the formula that we're going to use here is your Z-score equals your raw score minus the mean divided by standard deviation. So we have the raw scores, right? Here they are right there. The information that we need is we need the mean, and we need to calculate the standard deviation. So I'll do that the wrong way first. So once again, do not follow along on this. But let's just say that we are going to calculate it this way. So we got the mean, we got the standard deviation. We remember our formula. So mean equals average, open parentheses, highlight all those scores. We get an average of 15.2. Standard deviation equals STDEV. If you're doing population, it's .P. We are doing sample. Standard deviation here, so we don't even need the .S. That's how common standard deviations for samples are. So STDEV, open parentheses, highlight your cells, close those parentheses. There's our standard deviation. Now the wrong way to do this is to say, all right, we got those two pieces of information. Let me do a column of Z-scores. And what I'm going to do is, number one, and this is correct, number one, let's make sure we do the order of operations correctly. So we are going to have to open parentheses. So we put in equals, open parentheses. We highlight the raw score. From that, we're going to subtract the mean. So we have to do that first. That's in the numerator. Close those parentheses, and then all of that is going to be divided by the standard deviation. And we get a Z-score of 1.75. And we pop that into our answer cell. And lo and behold, we got that one correct. And we might say to ourselves, awesome, we did that correct, we got the correct answer. What I want to do now is I want to do that 9 more times. So I'm going to take advantage of that copy and paste, and I'm just going to copy and paste all the way down, and notice that something has gone horribly, horribly wrong. We can't copy and paste all the way down in this manner. And the reason for that is that if we double click on this, notice it's still accessing the correct raw score, but now it's moved down 1 row. So it's missing the mean, and instead it's putting in the standard deviation. And then when we divide by what we were hoping would be the standard deviation, we're dividing by an empty space, which is why we get this hashtag divide by 0? What? I can't do that. That's not possible. So this is the wrong way to do it. We cannot set it up this way. However, that's not to say that we're going to have to type this formula out 10 times or however many scores we have. But what we need to do is we need to think ahead and say, all right, I do want to be able to use that copy and paste function. So what we're going to do is we're going to set up what I like to call parallel structures, and we're going to set it up with another thing I like to call the cascading waterfall. So what we're going to do is we're going to have one column of means, and we're going to have one column of standard deviations. So we need to create a column of means and a column of standard deviations. And notice that we cannot even copy and paste these, because if we go average and then we highlight the all of the scores, notice that we get a mean of 15.2. And then if we copy and paste that down, oh no, look what happens to our mean. It goes crazy because once again, that formula is moving down with us. So we can't just copy and paste this way. We have to do one little move in order to create these parallel structures where we got 3 columns all with the right information. And the move is that in this first column, you calculate your mean. In this second column, we're going to use the equals function. And we're going to make that second column equal to the first column. Fair enough. Then what we do is we can copy and paste that equals function in the second row. Because right here we're saying make this cell equal to the one above it. Make the second row equal to the first row. And if we copy and paste that down one more, that says make that third row equal to the second row. And if we copy and paste that down one more, that says make the fourth row equal to the third row. Third row is equal to the second row is equal to the first row is equal to the mean. So in this way, we can copy and paste that all the way down, and we have an entire row now of means. That's exactly what we want. We want one entire row where it's all the same sample mean in this case. And then for the sample standard deviation, we're going to do the exact same thing. We can calculate the standard deviation equals STDEV, and then we highlight the scores that we want to calculate the standard deviation for. We hit enter. There's our standard deviation. Notice it's exactly the same that we did before. But now instead of copying and pasting that first row, we're going to do our cascading waterfall. We're going to make that second row equal to the first. And then when we copy and paste that, it makes the third equal to the second, fourth equal to the third, fifth equal to the fourth. And we can do that all the way down. And we have this waterfall of score of the mean, and we have a waterfall of the standard deviation. Importantly, we have it all the same in that those 2 columns. All right, so now we're set. Does everybody have these 3 columns set up the way that we got them right here? All right, perfect. So now we're ready to calculate those z-scores. Now we're ready to use that formula. So we go equals, open parentheses. We need those parentheses to do the subtraction, the deviation first. So open parentheses, highlight your raw score minus, highlight your mean, and all of that divided by. And if you're in this situation where you cannot click on the cell that you want, you have to use your arrow keys to kind of get that cell to where you want it to go, which is right there. Then we hit enter, and we have our mean of 1.7514. We pop that into the answer cells over here, and we see that we got that one correct. So just one more time, just to show everyone, we go equals, open parentheses, highlight the raw score, minus, highlight the mean, that's the top part, that's the numerator, close those parentheses, and all of that divided by, and then use your arrow keys to get to that. You don't have to go the long way around, but just use the arrow keys to get to that standard deviation. hit enter, and we have calculated the z-score for that one. Now you can take that and you can copy that formula and you can paste it all the way down. And you can see that it is continually accessing the correct information because we have it in every single row. We have it in every single, in the same position for every single raw score. That's what allows us to do this this copy and paste. All right, so before we even put these into the answer cells, let's say that we didn't have these automatic grading green cells down here. And we were doing this, let's say that this was part of our job. Let's say that we were working in that clinical psychology clinic and we were calculating z-scores and we just wanted to double check. We just wanted to make sure that nothing weird happened in our calculation. What can we do? What do we know about z-scores that will allow us to double check these z-scores we just calculated? What are two properties of z-scores that we know to be true?
Mean 0, standard deviation 1.
Exactly. So they should have a mean of 0. They should have a standard deviation of 1. So let's just check it. And I highly recommend do this in your exam. Let's just check it. Let's go equals average, open parentheses, highlight your z-scores, and we see that we have 1.77 to the exponent times 10 to the exponent minus 16. If you're not familiar with scientific notation, this is basically a very, very small number. This is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 1776. All right? That's super close to 0. That's as close as Excel is going to get. So that's the first thing you're looking for. You're either looking for 0 or that e to the minus, something, right? That indicates that it's very, very close to 0. Next thing we do is we calculate out our standard deviation. Equals STDEV, open parentheses, highlight your z-scores, and if we've done it correctly, we should get a standard deviation of 1, and we did. So this is just a nice little way to double check, just to make sure that, oh yes, we did, nothing went wrong, nothing went south. We did do this correctly. We got a mean close to 0, we got a standard deviation equal to 1. So that gives us confidence that when we do put all these into the answer cells, we already know we're going to get them all correct. So just a nice little double check you can do on the upcoming exam. Feel free to do that. I highly encourage it. And it just lets you know that, yes, we did it correctly. And as you can see, we have all those z-scores done. All right. Any questions on the calculation of part A, which is the z-scores? It's all good? All right. So the next thing we need to do is part B, which is a new standardized score with a mean of 40 and a standard deviation of 10. So we want to transform our old raw scores into these new scores with a mean of 40 and a standard deviation of 10. So the first move that we need to do is we need to transform our raw scores into z-scores. We just did that in part A. The next move we need to do is we need to take those z-scores and transform them into these new standardized scores. And the formula we're going to use for that is that our new standardized score equals our new mean plus the z-score multiplied by our new standard deviation. So that is that is the new one that they want. That is the new one that they want. That is the z-score that you just calculated. So that's what we're going to use. So we're going to, let's just label this stand X for standardized scores. And we are going to use that function. So once again, know what you're looking for. We're looking for the new mean, the new standard deviation. If you grab this mean and this standard deviation here, you're just going to reverse what you just did. You're going to take your z-scores and transform them back into the old raw scores. We want the new scores, the new standardized scores. So we have to enter in the new mean, which is 40, that's given to us in the question, plus the new standard deviation, which is 10, and then we multiply that by the z-score that we just calculated. We hit enter, and there's our new standardized score for that first raw score. So once again, we put in the new mean, which for this question is 40, and we get that right from up here. So we get the new mean, which is 40, plus the new standard deviation, which is 10, and all of that multiplied by the z-score that we had just calculated, and then we hit enter. And for this one, because we're providing the new mean and we're providing the new standard deviation, we can actually copy and paste that all the way down, because we're accessing only this column of z-scores. And once again, as you're developing your copy and paste skills, highly recommend just double click on one of the cells that you copied and pasted and make sure it's accessing the information that you want. So we want it to be accessing that particular z-score right next to it. Lo and behold, there it is. It's all good, it's all working, gives us confidence. All right, so we've calculated these standardized scores. Did we do it correctly? How can we check even before we put it into the answer cells? There's two things that we know that these standardized scores should have, and those are given to us in the question. Yes, they should have an average of 40. We were asked to create a new set of scores specifically that has an average of 40, so we can check that. We can calculate the average, and lo and behold, there it is, average of 40. What's the other thing that we know about these standardized scores? Their standard deviation should be 10. So we calculate out the standard deviation, and we get a standard deviation of 10. So even before we put them into the answer cells, we got very high confidence that we're going to get these correctly. Let's get these correct. Let's pop them into the answer cells. And we can see that Excel is not displaying all of the decimal points, just displaying the whole number. Notice, however, that it is being graded as correct, because what Excel is doing is it's not showing you all the decimal points. And if this is an issue for you, I know that I don't like to see it this way. What you can do is right up here, if you click on the Home tab, right up here under where it says number, you'll notice these two zeros, 0 going to 00 and 00 going to 0. These are the buttons you can click to increase your decimals and decrease your decimals. And you can do as much or as little, somewhere in between, whatever you like. But that's where you can get those extra decimals. So again, if it's bothering you, if it happens in your homework and you just want to see those decimal points, feel free, access those buttons up there and choose your level. But we can see that we have all of those correct. We've calculated out those standardized scores. All right, so just to give you some practice, there is 3 more questions on this, all about calculating out the z-score and then calculating out that new standardized score. And we will wrap up class time, and then we'll have a little bit of time for practice. Just a couple of announcements. So once again, here we go. So once again, we have, you got that practice sheet so you can practice these Z-score skills. And then we also have the homework assignment. So make sure that you find homework assignment number 5, chapter 2. It's in the Excel files, in the Canvas files folder. You're going to upload that to Canvas assignments. If I don't already have a place to upload that, I'll just double check after today's class. I'll make sure that you have one. Upload your completed Excel sheet, and that is due Wednesday, September 18th by midnight. Now on your homework, you'll see that it is, much like your other homework, where it is automatically graded. You do have as many attempts as you want, so if you don't get it the first time, give it another shot. Check to make sure that you're getting the correct means and the correct standard deviations. Use, very importantly, sample standard deviation and sample standard deviation is the one you're going to be using. Use those sample statistics. And again, try as much as you'd like. This is a growth opportunity, practice opportunity. Make sure you take advantage of it. I'm hoping that when people upload it, all I see is a whole bunch of 100% when I'm grading these Excel sheets. All right, and then there's a couple of reminders. Your Chapter 2 post-test, that is going to be due Wednesday, September 23rd at 10 a.m. Little bit of weirdness on that because of the exam. So I just want you to be aware of that. This is designed so that you will get feedback on your post-test and then still have 24 hours in order to use that feedback to prepare yourself for the exam. That's why we got that weird 10 a.m. thing going on. Please be aware of that. When the 10 a.m. deadline expires, that's when it's graded. So just be aware of that so that you don't miss that. And then just a reminder that if you are taking advantage of the pretest points to get 100% on your pretest, if you are taking advantage of the MyStatLab study plan and you're completing those mastery points, you will, the deadline for that is midnight before the exam. So your last chance to complete those mastery points for Chapter 1, midnight before the exam. Your last chance to do it for Chapter 2, also midnight before the exam. All right, so other than that, that's all I wanted to cover for today. So remember, next class, review session, student-driven, completely optional. A week from today, we're going to do the exam. And again, it's open book, open anything you want to use except conversations with other people. So I oftentimes find that students find it very helpful, especially for some of these exams, to have that step-by-step thing written out. So you are going to, just so that there's no surprises, there will be a question on order of operations and the use of the summation symbol. There's going to be questions on being able to read and unpack frequency tables and frequency distributions. You won't be making frequency tables, but I'll give you frequency table and a frequency distribution and say things like calculate the mean, calculate standard deviation. So you'll have to know how to deal with tables and frequency distributions. You'll have to know how to calculate the mean, median, and the mode. The sum of squared deviation, standard deviation, and variance for a sample. And then you'll need to know how to calculate Z-scores, and you'll need to know how to calculate standardized scores. That is it. So if you've got those down, awesome, you're good to go for the exam. If, for example, you're still, a little bit struggling with one of those, write it out for yourself, step by step. Say, have a little page just ready to go. Standardized score. What's your new mean? What's your new standard deviation? Here's the formula. Plug it all in. Easy peasy. So make sure you take advantage of it, because again, all I want to know is that you can do it, not that you haven't memorized. So just because this is our first one, I just want to make sure. I'm kind of driving it a little hard. I'll be quiet now, but just to make sure that everybody is aware of that, please feel free. Other than that, we're done for the day. So we got about 10 more minutes of class. If you got any questions, you want to stick around and practice, feel free. If that's enough stats for you today, you can call it a day as well.